Okay, so we're going to explore two more free body diagrams. In this next one we have a block with a mass of 4 kilograms being pulled with a force of 30 newtons at an angle of 20 degrees. Okay, and we're going to say that it's being pulled with a velocity of 3 meters per second. So it's kind of dragging along at a constant speed. Okay, and so I want to just create a free body diagram, and I want us to quantify all the forces acting. Okay, so we have this pull upward at an angle that we know that's going to be equal to 30 newtons. It's at an angle of 20 degrees, okay, above horizontal. We know that's going to have weight because it's on Earth, okay, and we now know that we can find the weight because we know its mass, and so the weight is equal to m times g, which in this case is 4 kilograms times 9.8 newtons per kilogram, okay, which gives us, we'll just round it to 10 for this one, so that would give us 40 newtons of weight. Okay, so I want you to determine what the other two forces are. So what other two forces are acting on this block? So pulling back, we should have a horizontal force of kinetic friction because it's sliding, and then we should have a vertical force, the normal force, of the ground pushing up on it. Okay, and so we know what this is and we know what that is, so we want to solve for the kinetic friction and the normal force. Okay, we can do them in either order. Let's solve for kinetic friction first. Since that is acting horizontally, we'll find the sum of the forces acting horizontally. So we could say, okay, in the positive direction we have this, the x component of this pull, so we'll say, we know it adds up to be 0 because it's moving at a constant speed. So this would be 30 times cosine of 20 minus our kinetic friction, and so kinetic friction then equal to 30 times cosine of 20, which would be, we get that kinetic friction is about 28.2 newtons. And then we're also going to solve for the normal force, so for this we'll do the sum of the forces in the y direction. We know those have to be equal to 0 as well because it's balanced up and down, it's not moving up and down at all. Okay, and so we're going to say we have this upward normal force and we have this upward component of the pull, so this would be 30 times sine of 20, and then we have this downward force of 40. Okay, so 40 newtons. Okay, so we'd say, okay, well the normal force then equal to, do a little bit of algebra, we add that over, subtract that over, that'd be 40 newtons minus 30 times sine of 20. Okay, so we want to solve this, we punch this in, we find that this is about 4.5 newtons, so it'd be 40 newtons minus 4.5 newtons, and so that would give us about 35.5 newtons. Okay, and so you could think about it that if you were just pulling straight along perfectly horizontal, the normal force would be 40 newtons, but as you start to pull up, you're kind of lifting it off the ground just a little bit. You're making it so it doesn't push down the ground as hard, and so the amount of normal force decreases. And if you look at this calculation right here, if we were to increase this angle all the way to be 90 degrees, then sine of 90 is 1, which means that if you're pulling up on this, if you're not pulling the side at all, just pulling straight up with 30 newtons, then the ground only has to pull up then with 10 newtons, alright, because 30 plus 10 would be 40. Okay, so you're again balancing it out there. Okay, so you can kind of maximize, or you can like kind of minimize the normal force by pulling straight up and down, and you would maximize it by pulling horizontally. Okay, so we're going to look at one more. This next one we're going to do is going to be a little bit trickier. And this one's going to be pretty important because we're going to run into a lot of situations like this. So we have this ramp here, and this block is sitting on the ramp. Okay, and what I want you to find is the normal force and the static friction. Okay, we'll say the ramp has an angle of 30 degrees. So we want to figure out, well, how hard is friction having to push to keep it on the ramp, and how hard is the normal force pushing it to prevent it from falling into the ramp. So the first thing we're going to do is we're going to draw a free body diagram. So we know that it has weight downward, and that's going to be m times g, right? So weight equal to the mass of 2 kilograms times 9.8 newtons per kilogram. Again, for this example, we'll round it to 10. So weight would be equal to then 20 newtons. Okay, so we have this downward force of 20 newtons. Okay, well, friction is going to be parallel to the ramp. Okay, and so we'll call this static friction. And then the normal force is going to be perpendicular to the ramp. And so there's the normal force. Okay, and so the trick to solving this question is that we could do it similar to the one that we did at the beginning, where we look at this angle and that angle and do two net force equations. But we can actually simplify this a little bit if we were to take our coordinate plane. Okay, so our coordinate plane, right, our xy plane is normally like this. What we can do is we can actually rotate our xy plane so that x is parallel to the ramp and that y is perpendicular to the ramp. Okay, and what that does for us is it makes it so that friction is all horizontal, normal force is all vertical, and then gravity is acting somewhere in between. Okay, and so the way that we might draw that, we're going to draw it a couple ways. We can draw it like this. So we have our friction, we have our normal force, we have gravity, and then we have our coordinate plane, so that's positive x, and this is positive y. And then we can solve for this, and then we'll talk about what this angle is in a second. Okay, the other option though is we can rotate the whole thing and have our coordinate plane be like this, x and y, and so have friction like this, have the normal force like this, and then gravity pulling at an angle. Okay, so real quick, we need to do a proof to show that that is the angle for gravity. So if this is our triangle, okay, and this is the gravitational force right here pushing down, and this is angle theta, which in this case is 30 degrees. Okay, well, we can draw another right triangle right here. Okay, so this is 90. Okay, this is 90 right here. Okay, so if this is 90 and that's 30, then this would be 60, or 90 minus theta. So we'll say this is 30, this is 60, which if these are complementary angles, I can't remember the term, but these add to be 90, so this angle here would be 30, which means that this right here is 30 and that right there would be 30. Okay, so let's go ahead and use this now to solve for those missing values. I prefer to work it out using this method right here. So we know that this angle right here is 30, so what we can do is we're going to have a component of gravity pulling it into the plane and a component of gravity pulling it down the plane. We're going to use this to balance it out. So we'll say, let's start with the sum of the forces in the x direction. It's going to add to be equal to 0. Okay, well, we have static friction pulling it up in positive x, so Fs, minus coming back down the ramp, we have this horizontal component of gravity, so it's 20 newtons times, since this now is the opposite side, it's 20 newtons times sine of theta. Okay, and so then static friction would be equal to 20 newtons times sine of 30 degrees, which I believe makes it 10 newtons of force pulling it up the ramp to keep it in place. Okay, and then for the y direction, to find normal force, those are balanced. Okay, so we have the upward normal force in the positive y, and then pulling back down we have this component of gravity, okay, that's going to give us 20 cos theta, okay, because it's the adjacent side, and so then the normal force equal to 20 cosine of theta. We can work this out, okay, and find the normal force is something like, let's do it real quick, so 20 times 30, oops, so we get about 17.3 newtons there, okay? And so this is one that we'll practice quite a bit in class. Okay, this is a scenario that we need to be able to analyze with our eyes closed. Alright,